This paper, Chain of Thought Empowers Transformers to Solve Inherently Serial Problems, delves into the intriguing concept of chain of thought prompting and its impact on the reasoning capabilities of large language models. What is the core argument presented in this paper?
The paper argues that chain of thought prompting, which involves instructing the model to generate a sequence of immediate steps, effectively empowers transformers to perform inherently serial computations. This is a significant advantage, as transformers, especially those with low depth, are typically limited in their ability to handle serial tasks.
That's an interesting claim. Can you elaborate on how chain of thought prompting enables serial computation?
Without chain of thought, the number of serial computations a transformer can perform is essentially bounded by its depth, which is considered fixed in this paper. However, by introducing intermediate steps, the model can effectively unroll the computation, allowing for a much larger number of serial operations. The number of steps in the chain of thought, denoted as T, can increase with the input length, while the depth remains constant.
So, essentially, chain of thought acts as a mechanism to extend the effective depth of the transformer?
Precisely. The paper demonstrates this by analyzing the expressiveness of transformers with and without chain of thought. They use the language of circuit complexity to formally define the capabilities of transformers in terms of the problems they can solve.
Can you explain how the authors use circuit complexity to analyze the expressiveness of transformers?
They define a new complexity class called COT, which represents the problem solvable by constant depth, constant precision transformers with a specific number of chain of thought steps, embedding size, and precision. This allows them to compare the expressiveness of transformers with different configurations.
And what are the key findings of their analysis?
The authors show that transformers with a constant number of chain of thought steps can only solve problems in a class called AC0, which is a subset of TC0, a class of problems solvable by parallel computation. However, with polynomially many steps of chain of thought, transformers can solve problems in P-poly, a superclass of P, which includes problems that are inherently serial.
That's a significant jump in expressiveness. Can you give an example of a problem that transformers can solve with chain of thought but not without it?
One example is the wording problem of the permutation group S5. This problem is known to be NC1 complete, which means it's widely believed to be outside of TC0. The paper shows that transformers with chain of thought can solve this problem, while those without chain of thought cannot.
So chain of thought essentially allows transformers to think step by step and solve problems that require a sequence of operations?
Yes, that's a good way to put it. The paper also provides empirical evidence to support their theoretical findings. They train transformers on 4 different arithmetic problems: modular addition, permutation composition, iterated squaring, and circuit value problem.
And what were the results of these experiments?
The experiment showed that for the problems that are inherently serial, like permutation composition and iterated squaring, transformers with chain of thought significantly outperformed those without it, especially when the depth of the transformer was low.
This is quite compelling evidence, but how does chain of thought actually work in practice? Is it simply a matter of
The paper highlights that the form of the chain of thought is crucial. They found that even incorrect reasoning steps in the few-shot examples can still improve performance. This suggests that the act of generating intermediate steps itself, rather than the specific content of those steps, is what unlocks the model's reasoning abilities.
That's fascinating. So it's more about the process of thinking step by step than the actual steps themselves?
Exactly. The paper suggests that chain of thought prompting encourages the model to engage in a more serial, step-by-step reasoning process, which is essential for solving problems that require a sequence of operations.
This research has significant implications for the development of more powerful and versatile language models. Can you summarize the key contributions of this paper?
The paper provides a theoretical understanding of the power of chain of thought prompting for transformers, demonstrating its ability to enable serial computation. They introduce a new complexity class to analyze the expressiveness of transformers with chain of thought and provide empirical evidence to support their findings. This research sheds light on the mechanisms behind chain of thought prompting and its potential for enhancing the reasoning capabilities of large language models.
This is a very interesting and insightful paper. It seems like chain of thought prompting is a powerful tool for unlocking the reasoning abilities of transformers. Do you think this approach will be widely adopted in future language model development?
It's certainly a promising approach, and it's already being explored in various applications. The simplicity and effectiveness of chain of thought prompting make it a valuable tool for improving the reasoning capabilities of language models. It's likely to play a significant role in future research and development.
Thank you for sharing your expertise on this fascinating topic. This was a very informative discussion.